office hours didn't disappear. Yeah. So, well, actually 3 to 4, because I may just want to go to the, science lecture series that they have today if they're having one. But so office hours 3 to 4 in my office, and 7 to 9 in the library AV center again, just like last week. So 3 to 4 in my office, 7 to 9 in the library AV center. So. All right. Now we're going to study the most wondrous system in all of quantum mechanics. Do I mean molecules? No, of course not. Do I even mean atoms? Don't be silly. The most wondrous system in all of quantum mechanics would be the quantum harmonic oscillator. And actually, in all seriousness, this is a really important system to study. I mean, not only is it a non-trivial application of solving the Schrödinger equation in one dimension, but it shows up everywhere. If you're talking about vibrational modes of molecules, for example, for small amplitudes, the potential is the harmonic oscillator potential. And so the vibrational modes of molecules are described by solutions of the harmonic oscillator.
And that's technically several degrees of freedom for
yeah. So it can, yes, you can basically go nuts with this. Also, if you have a crystal of atoms, it doesn't even have to be a crystal, but usually it's applied to crystals. Well, suppose I have a system like this: spring, mass, another spring, another mass, another spring, and they're both connected to a wall. And you say, classically, what are the ways this thing can vibrate? Well, if I pull this one 2 centimeters and this one 6 centimeters and let it go, they're going to do some really complicated, crazy kind of motion. But that can be analyzed as a sum of 2 very simple motions, namely the one where the 2 masses are going like this. If these springs here and here are of equal strength, if they're not, it's more complicated. But if these 2 springs are of equal spring constant, then you've got a simple mode where the masses are going like this, 180 degrees out of phase, and another mode where they're moving in phase like this. And every complicated motion you can generate is the sum of so much of this and so much of that. And each one of those, this is a simple harmonic oscillation, this is a simple harmonic oscillation, and so you can actually describe the system in terms of decomposing it effectively into 2 harmonic oscillators, even though it's this complicated thing. Take a crystalline material, you've got gazoodles of atoms, Avogadro's-ish number of atoms in there, and small vibrations around their equilibrium locations are, to a good approximation, described by spring-like displacements. The force is proportional to the displacement, or more quantum mechanically speaking, the energy is proportional to the square of the displacement, just like a spring has 1/2 kx squared for its energy. And it turns out that you can do a more complicated version of this. In other words, the system always has normal modes where all the atoms are vibrating at the same frequency in various configurations. The whole crystal would be all vibrating at the same frequency. The motions of the individual atoms could be quite complicated in relation to one another, their phase relations to one another and so forth. But, notice this had 2 normal modes associated with it. With your n atom system in 3 dimensions, it turns out there would be 3 n normal modes that could describe, by adding them together, every possible vibration of the system. And every one of those normal modes oscillates harmonically. So you can decompose your system into a bunch of harmonic oscillators. And classically you could do that. In quantum mechanics, though, it's quantum mechanics. So that means that instead of the atoms literally vibrating the way we think of them classically, instead what you get are excited states of the simple harmonic oscillator for each of the modes. And a so-called, and this will make a little more sense when we go ahead and do this, but a one quantum excitation of a lattice mode vibration has a name. Has anybody ever heard of what you call quantized lattice vibrations in a crystal? It almost sounds like photon, but there's one letter different. Phonon, yeah. A phonon is a one quantum excitation of a normal mode vibration in a lattice of atoms. So phonon energies are quantized, just like photon energies are. And you can talk about one quantum excitations, that's one phonon. Two is two quantum excitation, you have two phonons, and so forth. So you can actually quantum mechanically treat vibrations of a lattice in terms of phonons, and they're described in terms of the quantum harmonic oscillator. They are same as solutions that we're going to talk about here for the quantum harmonic oscillator. Photons are one quantum excitations of the electromagnetic field, which you can also quantize. If I make a box with, say, metal walls, and if I take the limit that the walls were perfectly conducting, the electric field has to be perpendicular to the walls at the location of the walls. Because if I have a metal wall and I had an electric field at the location of the wall that looked like that, well, that would mean there was a component of the electric field parallel to that metal wall. But if the wall is a perfect conductor, that would mean that you'd have essentially what amounts to a voltage across a superconductor, which would produce infinite current. You can't do that. You can't produce infinite current. So therefore, if you had a perfectly conducting wall, the boundary condition would be the electric field can only be perpendicular to it. And that leads to a condition on the wavelengths that can fit inside your cavity, similar to the way there's a condition on the wavelengths that can fit on between the ends of a tight-off string. So if you have a conducting cavity, then to a good approximation, the modes of the electromagnetic field that can exist inside that cavity have the property that there's an integer number of half wavelengths in each of the three dimensions if you have a rectangular box. And it turns out that each of those modes has a sinusoidal time dependence. The electric field at every point in space is just oscillating up and down as a sinusoid function of time. The different modes have different frequencies because you've got the relation that the wavelength times the frequency is the speed of light. So shorter wavelengths have higher frequencies. And classically then, you have all these normal modes, if you will, of vibration of the electromagnetic field inside the box. Quantum mechanically, you promote those normal mode oscillations into quantum harmonic oscillators. And a photon, in quantum field theory, is a one quantum excitation of a normal mode of the electromagnetic field. And in fact, quantum field theory basically, in the kind of this very standard treatment, essentially breaks fields into sums of harmonic oscillators. Only it goes crazy because there's a field associated with every type of particle. There's the electron field and the muon neutrino field and so on and so forth. And in quantum field theory, particles are actually one quantum excitations of the harmonic oscillator normal modes of the field associated with that kind of particle. So an electron is a one quantum excitation of the electron field. If there's two electrons, you've got two quantum excitation of the electron field and so forth. And so in the quantum field theory picture, you're consisting of a bunch of excitations of the electron field and the various quark fields that make up ordinary matter, of quark fields and down quark fields. And the fields interact with one another. We make these pictures of particles throwing little particles at one another, but it's all fields interacting with one another.
So we have very colorful fields.
What's that?
We have very colorful fields.
Yes, that's right. We have very colorful fields. Yes, red, green, and blue.
Yes.
Yes, that's right. Yes.
Exciting fields too.
Yes. Okay, well, I've gone a little far afield, and you know, it's,
Yes.
but, and you know, if to some extent you're saying, you know, based on, that's okay, because what I'm really trying to do is, first of all, maybe give you a little flavor of, wow, what is quantum field theory all about, just a little. But second of all, to convince you this is important. In other words, you know, not only is this just good practice in solving the Schrodinger equation, et cetera, but it has all kinds of application from molecules to quantum field theory. You can't overemphasize the importance of the quantum harmonic oscillator. And man, I wish it was named after me, but sadly enough, it is not. But I get to pretend that it is, so. All right. Any questions? All right. So, classical harmonic oscillator. You've probably seen this till you're blue in the face. We have a spring, which has spring constant K, and it's attached to a mass M, and it's displaced from its equilibrium location, and we let x be the displacement from equilibrium. And from Hooke's rule of thumb, I mean, it's not really a law. I mean, you know, you say Hooke's law for springs, but springs are more complicated than that. But for small stretches, it's a good approximation. Experimentally, the force is proportional to the displacement. So we say F is minus kx, minus because the force is opposite the displacement. If you stretch the spring, it pulls back. If you compress the spring, it pushes back. F is minus kx equals m d squared x dt squared. Right? So, you know, again, force is mass times acceleration. There's no physics there. The physics is in the fact that we can predict what the force is. It's minus kx. If I know x, I can predict the force. So all the physics is in the statement that F is minus kx. And then, and that combined with F equals ma tells you the motion. So there's no physics until you got the force law, coupled with the fact that, and then we claim that that force law lets us predict the acceleration. That's the content of the physics. So, d squared x dt squared is equal to minus k over mx, and then we define that to be minus omega squared x, where omega is the square root of k over m. So you need a function whose second derivative is minus omega squared times the function itself. It's a second order differential equation, so we expect two linearly independent solutions, and those solutions are, what are the two functions whose, well, what are two Li functions whose second derivatives are minus omega squared times the functions themselves, sine and cosine, right? Cosine omega t and sine omega t, and the general solution is a sum of those. So, solution is x of t is some constant a times the sine of omega t plus some other constant b times the cosine of omega t. How do you find out what a and b are in any particular case? Those are two unknowns, so you need two pieces of information. What are those usually given as? At time t equals 0, we assume we know what two things about our mass? Where it is and how fast it's moving. Yeah, its velocity, right? And in what direction. So yeah, its velocity. So if we know the initial position and the initial velocity, that gives us two equations in the two unknowns a and b, and we can solve. Note that you could also know where it is now and where it is 2 seconds from now. that would also be two conditions. They wouldn't be initial conditions, but you can also know 2 points along the motion, and that would be enough to determine it as well, or the velocity at 2 times. But usually we take it to be, we know where it is and how fast it's going initially. Of course, can we do that in quantum mechanics? No, because the uncertainty principle says you can't know where it is and how fast it's going at the same time. But that's okay. We'll see what to do there. What's the potential energy for a spring? Half kx squared. Yep, half kx squared. I'm not going to sit there and go through the derivation of all this here while you integrate the force dx with the minus the all that kind of stuff. We're just quoting results, but reminding you how it works. Potential energy is half kx squared. Oh, but wait, k is m omega squared. Right? K over m is omega squared, so k is m omega squared. So actually, for our purposes, a better way to write this is it's 1/2 m omega squared x. Omega is the natural angular frequency of oscillation multiplied by the mass after squaring it times a half and yes, right, and then multiply by x squared, and you will have the potential energy of the system there. So if I plot p of x as a function of x, what shape is that? It's a parabola. Yep, it is a parabola. So generically speaking, v of x is a parabola. And how big m and omega are, or how big k is ultimately, is what's going to decide whether that's a really steep parabola or a really not so steep parabola. The stiffer the spring, the higher the energy rises as I displace it. So you get a parabola, and quantum mechanically then, well, okay, so then the total energy is going to be equal to what then, classically speaking? The kinetic energy is what? Not in terms of this V stuff, because we want to put it in terms of the momentum, because that's the operator that's going to show up in quantum mechanics. So what's it? The kinetic energy is p squared over 2m, yep, so the energy is p squared over 2m plus 1/2 m omega squared x squared. That's the energy. And then we say, what quantum system how would we describe this thing quantum mechanically? And the answer is, wherever you see an x, put an x. And wherever you see a p, put a minus IH bar ddx. So in other words, now, let's promote it. I'm probably not going to keep doing that, but let's promote it to h. H is going to be equal to, well, p squared over 2m is what we got for the infinite square. Well, it's always this minus h bar squared over 2m d squared dx squared, because a p is represented by, it's an operator, so I guess it'll have a little flag on the top of it. P is represented by minus IH bar ddx, so p squared is minus h bar squared d squared dx squared. So h is going to be, as an operator, minus h bar squared over 2m d squared dx squared plus 1/2 m omega squared x squared. Because x just stays as x. So, if I want to write down Shrek for going to be for the full time-dependent version, I h bar d psi dt equals h psi, but we know what h is. So it's equal to minus h bar squared over 2m d squared psi dx squared plus, I know what v of x is. It's 1/2 m omega squared x squared multiplying psi of x and t. So that's the equation we want to solve to describe the quantum version of the simple harmonic oscillator. That's our partial differential equation. And if we separate variables in the usual way, the time-independent Schrodinger equation is always h psi equals E psi, because by definition the eigenvalues of H are called energies E. Do you have a question, Ben?
Is that still supposed to be x squared?
Yes, thank you for saying that. Yes, it very much is. Yeah. Subscripts, superscripts, are easy to mess up. Yeah, so yeah, it's definitely supposed to be an x squared. So thanks for pointing that out. H psi is equal to E psi, or in other words, minus h bar squared over 2m d squared psi dx squared plus 1/2 m omega squared x squared psi of x is equal to E psi of x is the time-independent version of the equation. So our task will be to find the psi's that satisfy that relationship. And we're going to do something really clever in order to do so. It doesn't look so bad, but it turns out it's not trivial to solve that equation right there. You can't just guess the form of the solutions of that equation. But that's what we're trying to solve here. Now, how many of you had differential equations class? So most of you have. So, well, maybe not, but your first inclination on seeing an equation like that, well, it's first to try to guess the solution. And so you spend a while doing that and realize, okay, well, it's first to look it up in the book. Okay, pretend you don't have a book around, okay? So if you're a mathematician starting from fresh trying to solve that, first you see, well, can I just guess some function that solves it? And the answer is, try as you might, no. So then you say, okay, let me just assume that I can write psi as a power series. So you write it as a power series, powers of x, and you plug the series in to the equation, and then you find relationships between the coefficients in the series. And that gives a representation of the solutions which is kind of formal. You know, in other words, you can't just look at it and visualize what it looks like. But on the other hand, it turns out that if you're a good mathematician, you can make headway with that and then start classifying the solutions and graphing them and so forth. And I'm happy to report we're not going to do that here. We're going to do something which you would never think of, or if you would, you're going to win the Fields Medal someday, or a Nobel Prize or something. I don't know who thought of this, actually. I should look that up, but they were smart. It's not hard. It's not too hard to follow. It's one of those things where, well, you know, it's harder to come up with than it is to do it. You know, I mean, I understand calculus, but I don't think I would have invented it, you know. Sad to say. It is, however, how I'm confident that I'm not the only thing in existence. Because, you know, you kind of say, the only thing I can really be sure of is that I myself exist because I think and therefore I am, you know. So how do I know that there's anything else out there besides me? Maybe you guys are just these elaborate figments of my imagination. I mean, I like you, but maybe I'm just imagining, you know, these wonderful people and so forth, and they're not really out there. Or maybe you guys are really just robots. They're cleverly programmed, and you give the appearance of sentience, but, you know, I'm just in the matrix or something, you know. Well, I know I'm confident there's somebody else out there because, A, I know calculus, therefore, there must be another mind out there that invented it so that I could learn it. And I'm more willing to think that somebody else taught me calculus, somebody else invented it, than I am to hypothesize that there's an area in my mind that's so smart it invented calculus and then taught it to the rest of me, and I had no idea this was going on. So that's how I'm confident that at least somebody else is out there. Maybe it's not you folks, but at least somebody else is out there. Now, let me clarify. I do think you guys are out there, you know, but still, it's just a strong suspicion. I'm not sure 100%. But I would bet my rent money that you are. Anyway, what we're going to do is something that's going to at first look insane, but it's not. It's actually inspiring. So, we can do the following. We can write that h is equal to, this part isn't going to look insane, 1 over 2m p squared plus m omega x, the quantity squared. And that's not crazy, that's just one little factor in there. Yes? Yeah, remember, p squared is the operator minus h bar squared over 10 d squared to the x squared. So if you like, because it's m squared over m. Yeah, m squared over m. So that time I was right with my superscripts. Which, if p and x were just ordinary numbers, and by the way, in operator theory, ordinary numbers are called C numbers sometimes, versus operators, which are called Q numbers. But if these guys were just ordinary numbers, that can be factored as h is equal to h bar omega times the quantity. Here's where it's going to start looking like, why are you doing this? But bear with me, it will pay off. 1 over the square root of 2m h bar omega times, in parentheses, plus ip plus m omega x, close parent, close square bracket, times 1 over root 2 m h bar omega minus ip plus m omega x, close parent, close square bracket. So if you just think of p and x as ordinary numbers, if you multiply this out, you'll find that it is in fact what's up here. Because when I multiply the things in the regular parentheses, if I take minus ip times plus ip, what's that equal to? P squared, right? Because minus I squared is 1. And then they're going to get a m omega x to quantity squared. And then the other pieces are going to cancel. I'm going to get minus ip m omega x plus ip m omega x. So those pieces would cancel. And then over here, I'll just have 1 over 2 m h bar omega times h bar omega. So I'll just have 1 over 2m out of all of that. So sure enough, this does factor into this expression if p and x are just ordinary numbers. So it looks crazy, but on the other hand, it turns out to be useful. We're going to call this operator, because p is an operator, it's not just a number. We're going to call this operator right here a minus. And this slightly more intelligent operator is going to be called a plus, because it got a higher grade. They're both pretty smart, but this guy's just a little smarter than the other one. bar ddx, minus I h bar ddx, and multiplying a function by x and then taking its derivative isn't the same thing as multiplying the derivative by x, which means order matters here when we think of these guys as operators. So I was very careful when I did this multiplication. Notice that I get a plus I m omega are just numbers, so those can move out, plus I p times x minus I x times p. So that xp comes in with the minus sign, and the px comes in with a plus sign, because there's two minus signs right there. And it is important. I'll slow down if you want to catch up. And any questions? Now this beast right here is called the commutator of x and p. And it gets the symbol square brackets x comma p. That's the commutator. I like that name. The commutator. Makes me think it like makes like French fries or something, you know. It's, the commutator.
Connoisseur right there.
Something along those lines, yes. The commutator. Most of you may not remember a restaurant called Burger Chef. It has gone the way of the dinosaur now. But they had two characters, Burger Chef and Jeff, when I was a kid. They would advertise for Burger Chef, this fast food place. And they would have these ads where they talked about how delicious their French fries were because they used the tater computator, which is why commutator makes me think of making French fries, because I remember the tater computator from the old Burger Chef commercials. Yeah, so I'm glad I could share that.
Made out of a potato.
No, it precisely computes how to make optimally delicious French fries.
Oh.
Tater computator.
Okay.
Yes. I'm hungry right now because I didn't have lunch and now I want French fries. But anyway, it's the commutator of x and p. And in general, if I've got two operators a and b, then the commutator of a and b is by definition ab minus ba. A guilty pleasure, musically speaking. Because I don't know if you guys know what I'm talking about with that, but but anyway. In other words, it's the difference between what you get when you apply b first and then a, and what you get when you apply a first and then b to a function or whatever it is that they're being applied to. Not necessarily zero for operators. Because the order of operations matters. So let us calculate what is the commutator of p and x, of x and p, I should say. How do you do that? Well, you just imagine having them chew on a test function and see what happens. So let's find out what the commutator of x and p applied to f of x is going to be. Well, that says p, remember, is minus I h bar ddx, and we're in one dimension, so I can just call it a total derivative here. So that'll be minus I h bar x ddx of f, because I first apply p, in other words, I first take minus I h bar df dx, I apply p to my test function, since P is minus IH bar d dx, applying it to F means minus IH bar dF dx. First I apply P, the first thing you apply is well, yeah, I'll write one more line here. So, note that's going to be x P on F of x minus Px on F of x, but then we have to remember these are operators, so that'll be minus IH bar x dF dx, because first I hit it with P, then I multiply by x. First I differentiate, then I multiply by x. But over here, I take the derivative of x, f of x. So this term gives plus IH bar d dx of x times f. Plus because it's minus IH bar d dx here. So it's minus IH bar d dx of x f of x, because P is being applied to x times f of x. Okay, any questions about that? So, minus IH bar x df dx is what the first term stays. Here I can use the product rule. What's d dx of x f? Yeah, it's derivative of the first times the second, plus the first times the derivative of the second. So it'll be dx dx times f. What's dx dx? 1 plus x df dx. So this is going to turn into plus IH bar f from the derivative of x times f plus IH bar x df dx. All that because d dx of xf is, get long-winded, dx df times f plus x times df dx. But dx dx is just 1. And then you've still got IH bar hanging around for kicks. So then, notice those terms cancel, but you're left with IH bar f. So in other words, the commutator isn't 0, because when I applied it to f of x, I got IH bar times f of x. So what we say is that the commutator of x and p is equal to IH bar, because the commutator is an operator, and when you apply it to a function, you're multiplying the function by IH bar. It's entirely equivalent to simply multiplication by IH bar. If you really want to get pedantic, it's IH bar capital I. What is capital I? It's me, but what else is it? It's the it's the identity operator, right? If you really want to be technical, it's got to be an operator, so that's really the identity operator. But the identity operator is equivalent to multiplying by 1, so we don't usually make that distinction. But if you want to get all fancy, you need something to put a hat on. So, therefore, you throw in the I there. This is so important that it has a name. It's called the canonical commutation relation. That's another good name. Yep. The canonical commutation relation is that the commutator of x and p is IH bar. So it's like, phone your parents, right? You say, today in quantum mechanics, we studied the quantum harmonic oscillator, and as part of that learned that the commutator of x and p is xp equals IH bar, and that's called the canonical commutation relation. You are going to sound so smart. Your parents are going to think like, wow, our money is so well spent educating our child. We are just busting with pride. So I suggest that you do that.
Unless your parent is a physicist.
Yeah, right, that's right. Then they'll be like, well, it's about time. I learned it in kindergarten. Yeah, yeah. We had Peter Freund at the University of Chicago, physicist extraordinaire who sang opera as a hobby. Was very fond of saying, and so, as you learned in kindergarten, no matter how complicated it was, and this made him very intimidating because we thought he meant it. We thought he probably did learn it in kindergarten. And I'll never forget when I was taking ordinary mechanics, not quantum mechanics with him, and he starts going over the properties of a vector space. I think I've told some of you this story before. He goes over the properties of a vector space, and he's basically just assuming the properties of a vector space when talking about classical mechanics. And then at one point he goes, oh, I'm very sorry. I keep saying by the properties of a vector space, but it occurs to me, maybe some of you don't know what a vector space is. Is there anybody who needs to know what a vector space is? And my friend Mike Leibig meekly raised his hand, and Peter Freund says, it's trivial. A vector space is simply an abelian group with an addition defined. And then he just kept on writing. And so that sort of defines them for me, along with, as you learned in kindergarten, and then it's just, like I say, we think he probably did learn it in kindergarten. So, well, that's my very bad Austrian accent, very horribly bad, terrible Austrian accent. Yes. Or something, Austria-Hungary or something. I don't know exactly what it was, because it didn't sound quite German. But he sounded kind of like, I don't know, Count Dracula sort of. So, but more German than that. He will never see this, right? But anyway, but he was great, right? I'm singing his praises. He learned these things in kindergarten. Here's why this is important. The fact that X and P don't commute is what's responsible for the uncertainty principle. And so this is fundamentally what is making quantum so weird for us, essentially. This is what leads to the uncertainty principle, as we will see. It's the fact that X and P don't commute, which means that you can't know both of them simultaneously. Because if two operators do not compute, if two operators do not commute, it's pretty easy to show that you cannot find a complete set of eigenfunctions that they have in common. And that means that in general, eigenfunctions of one of the operators won't be eigenfunctions of the other. So that, for example, X and P don't commute, that means the eigenfunctions of X are not eigenfunctions of P, and vice versa. So if you measure the position and snap the system into an eigenfunction of the X operator, it won't be an eigenfunction of the P operator, and therefore you won't know what you're going to get when you measure the momentum, and vice versa. If you measure the momentum and snap the system into an eigenfunction of the momentum operator, you're not going to know what you're going to get when you measure X, because that won't simultaneously be an eigenfunction of X, and so it won't simultaneously have a well-defined position. And given the time, I'll say that that's what we'll show immediately first thing on Tuesday. It's very easy to show. The fact that X and P don't commute, or in general two operators don't commute, means they can't have a complete set of eigenfunctions in common. And it's essentially because if they did, the difference between applying one and then the other, and then in the other order would always be zero. But by hypothesis, you don't always get zero when you switch them. And so it's actually quite easy to show. And so, in a sense, this is fundamental. It's sort of everything follows from this relation right here in quantum mechanics, that XP commutate to IH, or commute to, well, don't, whatever, they commutate, right? So we say they don't commute in that case. If they do commute, the commutator is zero. Then you say they're commuting operators, because they take the bus to work or something like that. Oh, and by the way, Dr. Mack is going to, oh shoot, I'm supposed to announce this. Dr. Mack is having the first PH squared on, I think it's early next week or something. I'll send you, well, he's going to tell you. But anyway, be alert for PH squared. It's coming up. There's going to be free pizza. It's going to be great. There's going to be fellowship and all that sort of thing. Oh, yeah. PH squared is, we have the physics, food, and fun. So he's adding PH fellowship to that, so some extra meetings of physics students. So he didn't want to call it PH to the fourth, so it's PH squared. Physics, food, fun, and fellowship. However, it turns out that people just taking physics classes, surrounded by physics majors, are welcome to enjoy physics, food, fun, and fellowship too. So in other words, you should show up too.